Hi everyone, myself M. Chandra Pratap Reddy from the Department of Electronics and Communication Engineering, studying in Srinivas Ramanujan Institute of Technology, Anantapur. Today we are discussing about design and simulation of a 4-bit ring counter using Verilog Code. Design and simulation of a 4-bit ring counter using Verilog. This presentation explores the design and simulation of a 4-bit ring counter using Verilog HDL is a hardware description language widely used in digital circuit design. Introduction to ring counters. Sequential circuits. Ring counters are a type of sequential circuit used in digital electronics for various applications. Data shifting. They function by shifting data through a chain of flip-flops, creating a circulating pattern. Counting and timing. Ring counters can be used for counting, timing, and generating a specific timing sequences. Applications. They are used in applications like frequency division, digital clock circuits, and signal processing. Fundamentals of Verilog HDL. Hardware description language. Verilog is a powerful language for designing and simulating digital circuits. It allows for creating models of hardware components like flip-flops, gates, and memories. Behavioral and structural modeling. Verilog offers two primary modeling styles, behavioral and structural. Behavioral modeling describes the functionality of a circuit, while structuring behavior modeling defines the circuit's interconnection of components. Simulation and verification. Verilog enables the simulation and verification of designed circuits. Simulation allows for testing the circuit functionality before actual hardware implementation. Designing the 4-bit ring counter in Verilog. Flip-flop chain. A 4-bit ring counter consists of 4D flip-flops connected in series, with the output of each flip-flop feeding into the next clock input. The flip-flops are triggered by the common clock signal, causing data to shift through the chain. Feedback path. The output of the last flip-flop is fed back as the input to the first flip-flop, creating a closed loop. This is the 4-bit ring counter program, that is module ring counter. Input clock, input reset, output reg of 3:0 Q. Always at the rate positive edge clock or positive edge reset. Begin if of reset Q less than or equals to 4-bit binary of 1,000, else Q less than or equals to Q of 2:0, Q of 3. End module. Behavioral modeling of the ring counter. Initialization. The initial state of the flip-flops is defined using an initial block. Data shifting. An always block describes the data shifting logic for each clock cycle. Output assignment. The outputs of the flip-flops are assigned to appropriate signals. Structural modeling of the ring counter. Structural modeling. Interconnection of components. Initiated the flip-flops. Create instances of the flip-flops as separate modules. Connect outputs and inputs. Connect the outputs of the each flip-flop to the inputs of the next. Feedback path. Connect the output of the last flip-flop to the input of the first. Simulation setup and test bench. Test bench design. A separate test bench module is created to test the ring counter. Stimulus generation. This test bench generates clock and reset signals to drive the ring counter. Signal monitoring. The test bench monitors the outputs of the ring counter to verify its functionality. Analyzing the simulation results. Correct punctuality. The waveform shows the expected sequential pattern of the ring counter timing behavior. The waveforms demonstrate the timing characteristics of the counter verification. The simulation verifies the design correctness and validates its functionality. Applications and use cases. Frequency division. Ring counters can be used to divide a clock signal frequency. Digital clock. They can generate timing sequences for digital clock circuits. Signal processing. Ring counters find applications in various signal processing tasks. Thank you.